Welcome to my Physics Lab 2 projectile motion. For this lab, we were tasked with throwing an object in the air like a projectile and then track the data using Tracker. Then we were to do coding, and here we create two computational models of the experiment, one with only the force of gravity and then another with the force of both gravity and drag. And the purpose of this experiment is to explore Newton's second law and the principles of physics. Here's a preview of the results, with all three being very similar, especially the two computational models, and then the blue one here at the top is the experimental data. For this experiment, the system is the paper ball that we used, and the surroundings is everything else, and what's important to us here is the earth and the air. The first important physics fundamental is Newton's second law, which is used to derive the velocity update formula, seen at the bottom of the screen. The next important physics fundamental is the position update formula, which, along with the velocity update formula, works iteratively as time progresses. The two forces acting on the paper ball are gravity, which is caused by Earth, and drag, which is caused by the air. This is also known as air resistance. Here's our video. One more time. Now I will go over the computational models which were made using GlowScript. Here are the initial conditions with the mass of the paper ball in kilograms, position in meters, and velocity in meters per second. We found B, the drag constant, by inputting different values until we found one that outputs a similar result as our experimental data using trial and error. This is for the model with drag and gravity. For the model with only including gravity, B equals 0. Here is the calculation loop of the coding, which includes both the force of drag and the force of gravity. Also, this includes the velocity update formula and the position update formula, which iteratively track the ball. Here are the trajectories of the computational models. While they are very similar, they are not the same, which shows how small the drag force is in terms of its impact on the ball. Now, I will be comparing these computational models to the experimental results. Here are the results in terms of x and y, starting from the right, going left, as this is the way we threw the ball. At the top of the graph in blue is the experimental results. The orange is a computational model using only gravity, and the green is the computational model considering both gravity and drag. The computational models are not the same as the experimental results, which could be for a number of reasons. The biggest reason is due to human error, as I could have tracked the ball poorly using Tracker or found a bad value for B using Guess and Check. Imprecision is likely to cause issues when using Tracker and creating the code. Also, the shape of the ball could cause it to travel differently than a true ball, as it could catch air inside the paper and not encounter drag normally. When observing the velocity versus time graphs, it is clear that terminal velocity is not found in either models, because the velocity never gets to a certain value and evens out, but is continually changing until the end. A similar experiment could be to drop an item from a higher height or with a higher velocity, and then record the velocity as it falls. In this situation, it should end up leveling out to a terminal velocity. If the object were thrown straight in the air with the same initial speed, it would take longer to reach the ground. In this experiment, only a component of the speed was in the y direction, while the full speed would be in the y direction in this instance, which makes the initial velocity in the y direction greater. According to Newton's second law, it can be determined that the higher initial velocity means it will take more time to reach the ground. Thank you for listening.